Let me show you some images. They all relate to the night store problem. This is meant more to entertain than to educate. I first came across a webpage by Donald Knuth. He had been invited to design artwork for the walls of the university building, and one of the featured patterns was the one on the right. Knuth credited George Ellis as one of the foremost experts on the subject. For over 50 years, Ellis has been collecting an archive of remarkable night tours, while continually adding his own tours. All I had to do was choose the patterns and animate them. The problem is easy to state. Can a knight visit every square of a chessboard exactly once? You already know the answer, but try finding such a tour yourself. There are quadrillions of them, yet constructed even a single one is far from easy. Later we will mention a useful algorithm. One small note: if the knight can return from the final square to the starting square in one legal move, we'll draw the pass as a closed loop, simply because it looks nicer. Let's begin with tours that have central symmetry. I've shown the yellow one before, and it has become surprisingly popular ever since. As you can see though, there are many more constructions of the same kind. This symmetry means that a 180-degree rotation about the center of the board maps the pattern onto itself. But what about 90-degree rotational symmetry? Do you think such tours exist? On a 6x6 board they do. Here's animation. We've already seen central symmetry. Naturally, the next question is whether mirror symmetry exists. The tours in this animation are almost symmetric about the vertical axis. If you look closely, the reflection is slightly different from the original. We can also create patterns that are almost symmetric with respect to two axes at the same time. And don't forget about diagonal symmetry. Or rather, almost diagonal symmetry. There are still tiny differences, but they are remarkably close. The first person to study the night tour systematically was Euler. He devoted months to the problem and devised an algorithm for constructing tours, anticipating graph theory. What's more, Euler's work contains an impressive collection of centrally symmetric tours, far more than anyone before him. But was he actually the first to solve the problem? The earliest known references most likely come from China, more than 4,000 years ago. The earliest known tours on a standard chessboard date back to the 9th century. Notice that the pink tour is closed. That means you could start from any square and still obtain a valid solution. The orange tour was encoded in poetic form, or rather half of it, say the lower half. In the 14th century the problem was forgotten, then rediscovered in the 18th century, when chess gained enormous popularity in Europe. Even so, many of these patterns still closely resemble their Eastern predecessors. By the way, you may recognize the author of this particular tour. Remember de Moivre's formula from complex analysis. Representing night tours as polygonal paths is actually a relatively recent idea. The earliest examples appear in the work of the Italian mathematician Lelio Dalla Volpe, the image on the left. On the right is a pattern created by the mathematician and musician Alexander Vandermonde. An excellent algorithm for constructing night tours was later published by the chess enthusiast Warnsdorff. The idea is simple: at every move choose the square from which the knight will have the fewest possible onward moves. Roughly speaking, it's advantageous to traverse the edges of the board first, and only then move toward the center. A bit of street magic now. Let's number the squares in the order the knight visits them. Can we turn the result into a magic square? A semi-magic square is possible. Here's animation. The sums of the numbers in each row equals 260, and the same holds for each column. It's only the diagonal sums that differ. Here are 8 more semi-magic tours. Notice the dates, long before the computer era. The last 3 tours were created by a 19th century Indian Maharaja. Our next collection of 8 tours comes from Karl Friedrich von Janisch, a chess master, chess theorist, chess composer, and mathematician who lived in St. Petersburg. He excelled in mathematics and theoretical mechanics, while also popularizing chess. He was a world-class player. The original problem can be strengthened in another way. Once again, number the squares in the order the knight visits them. Now focus on the numbers highlighted in yellow. It turns out a knight can visit them in sequence. George Ellis particularly values this find among his collection, since the picture resembles a projection of a cube. And here the squares of natural numbers literally form a square. The cover of the 1971 issue of the Soviet magazine Kvant features a tour like this. Rather charming, isn't it? Here are a few more tours with unusual properties. Can you guess what's special about the first 2? The yellow tour contains 37 moves along parallel lines, meaning that one particular slope occurs as often as possible. The pink one has 34 such moves, but the tour is closed. The orange one, by contrast, has a slope of -half that's used in only a single move, in the upper left corner. The last picture contains 14 right angles. The other patterns also hold interesting ideas related to angles and directions, but let's move on. What other mathematicians had a hand in the knight's tour problem and its associated patterns? Gaspar Monge published quite a few beautiful centrally symmetric tours. In this scene you will also spot the name Dudeney, the mathematician and a famous puzzle creator. Take a close look at his tour. It naturally splits into 4 parts, and each part is itself a valid knight's tour on a rectangular section of the original board. Dudeney also explored tours on odd-sized boards. These produce elegant patterns that are easy to generalize. Simply increase the board dimensions by 2 squares and you get a new loop of the same type. There are also several remarkable tours by Legendre, the French mathematician who made fundamental contributions to number theory, and the only mathematician of such stature whose actual portrait hasn't survived, only watercolor caricature remains. And many other authors of tours are fairly well known, all connected in some way to mathematics or chess. Let's mention Donald Knuth once more. He wasn't the only one fascinated by the question of how many knight's tours exist. It's a beautiful problem in combinatorics, and the complete answer was found only relatively recently. Do you know who was the first to compute the total number of open knight's tours? The answer is the author of the pattern in the lower right corner, Alex Chernov. The patterns you're looking at now work like this. The knight doesn't visit every square, but the tours have no self-intersections. It seems still unknown what the largest number of squares of an n by n board is that can be covered by a non-intersecting path. For small sizes, computer search gives the answer, but beyond that, it's unclear. And finally, here are a few more patterns from the same family, this time with rotational symmetry. Think critically, do math, take care.